Hey guys, in this video we will be going into inferences on counts now. So before we've worked with means and proportions, now we're working with a new type of data called counts. So all of these different kinds of data are kind of derived from your raw data. For proportions, for example, you take your raw data over some total number to get a percentage or some decimal number that represents a proportion of a population. For means, what you do is you take your raw data and then you average it all together to get some average value. But for counts, that is working directly with the raw data, so we don't do any manipulations to it. So an example of a proportion would be some 9% of a population born in December. The means could be the mean age of a bunch of people when we take samples out of a school. And then our counts, though, would just be the direct number of, for example, freshmen in a high school. Or in the other two examples, your counts would just be the number of people born in December or the number of people that are 16 in a school. So here is a scenario where you would have to work with the counts. So let's say you randomly select a bunch of CEOs and record their zodiacs in a table. Are certain zodiacs more likely to have CEOs born in them? So you can see here that everything is set out in a simple table. We have the signs, so the categories on one side, and then the counts belonging to each category on the other side. And what we're going to do is we're going to do some math on these counts to find out if the variation between categories happened by chance. So one of the most important numbers that we need to pay attention to is our expected value. Generally, your expected value will be the total number of people over the number of categories. Going back to our CEO example, there are 256 CEOs in this table. And so if we assumed that zodiac sign and whether or not you're a CEO have no association whatsoever, then that means that there should be an even distribution of CEOs between zodiac signs. So that would mean that these 256 CEOs would be spread out evenly over our 12 zodiac signs. 256 over 12 would be about 21.33. So in this case, 21.33 would be the expected value for each of these categories. So in our perfect universe where we can somehow have decimal CEOs, then under the condition that there is no association between zodiac sign and CEO births, then there would be 21.33 CEOs out of the 256 born under each zodiac sign. So with our inferences on counts, we bring in a new type of test statistic. So our test statistic is just whatever ultimate score that we're looking for. For example, the z-score is the test statistic for proportions, and the t-score is the test statistic for means. For counts, on the other hand, our test statistic is called the chi-squared statistic. I did not spell it wrong. CHI is actually pronounced chi, as in the Greek letter. And this is not an X, this is a chi. So our chi-squared is equal to the sum of, and then going through every category, the observed data minus the expected value squared over the expected value. With this question, we already know that our expected value for every category is 21.33. Everything here is what we got when we went out and sampled, so this is our observed data. So in order to get our chi-squared statistic, for each category we would take the observed data minus our expected value here, square it, and then divide it by 21.33 again. So writing out the first two terms, that would look like our chi-squared is equal to, looking at category 1, our observed data is 23. So 23 minus 21.33 squared over 21.33. And we have to do this for every single category. So now we go into 20. So plus 20 minus 21.33 squared over 21.33. And we would do this for the remaining 10 categories. So you would continue adding up every category until you get to the last one of 29 minus 21.33 squared over 21.33 to get your final chi-squared value. And that would be equal to about 5.09. So as always, we have our conditions again. We have 5 conditions this time because we have to add on a condition that our data is counted. So we just say, yes, our data is counted, the condition is passed. You don't really need to prove it, you just say, yeah, it's counted. Then you have your independence, so whether one person is a CEO should not affect if another person is a CEO. They have to be randomly selected or at least representative of the population. You have to sample under 10% of the population. And then our large enough condition is a little bit different now. there must be a value of at least 5 inside each cell. So what a cell is every little box in our table. In this case, this is a cell, etc. But when the condition says that the cell value must be larger than 5, it's not talking about our observed data. We're not looking at this one. What we are looking at is the expected value. So the expected value must be greater than 5 for each cell. It doesn't matter what the observed data is, we only care about the expected data for this large enough condition. So here are the steps for our hypothesis test. You will note that the name of this test has again changed and the format is a bit different from what we've used before. This one is called a chi-squared goodness of fit test. Chi-squared tests have different names based on what kind of purpose they're used for, but the general mechanics for it is all the same. Besides a chi-squared goodness of fit test, there's also a chi-squared test of independence, etc. So what you do in a chi-squared goodness of fit test is you're basically going and seeing if there's any real difference or specific pattern to the data. For a chi-squared test of independence, what you're looking for is whether or not the data is independent. It's pretty straightforward. So the steps for our hypothesis test is basically the same. Our first one is again always our POI. And then for our step 2, this is our important numbers in our hypotheses. Our null hypothesis will always be basically the same, but in this case for chi-squared tests, you can write it out either as words or in mathematical notation. If you're going to do it in words, then you can just say that whatever variable is evenly distributed. So for our CEO's question, it would be our null hypothesis is CEO births are evenly distributed between zodiac signs. If we wanted to write that out in math terms, it would be the proportion of CEOs born with this zodiac sign is equal to the proportion of CEOs born with this zodiac sign, and then you would do the same for all 12 zodiac signs. That would be a bit long, which is why we usually stick with words. So our null hypothesis is even distribution. Our alternative hypothesis now is always going to be the same. It's just that if the null hypothesis is even distribution, then the alternative hypothesis will be that it's not evenly distributed. Depending on what kind of instructor you have, the third step may or may not be optional, and it is to take your table and make a bar chart with it. So you would make a bar chart with, for our CEO question, the x-axis being all the different zodiac signs, and then the y-axis being how many CEOs have that zodiac sign. And then you would include a horizontal line through the bar chart, marking off where your expected value is. So it would look something like this. This is just a rough sketch, but if this is your bar chart, you would mark off your expected value just as a dotted line through. And then you check your conditions. So counted data, independence, randomization, 10%, large enough. Once you have passed the conditions, you can calculate your chi-squared statistic. So you use your formula and you sum up your observed data minus your expected data squared over your expected. And with your chi-squared statistic, you can use your calculator and use a new calculator function to get your p-value. So again, our ultimate goal will always be to find that p-value, but now we're using a different function. Now instead of norm CDF or TCDF, we have chi-squared CDF. So chi-squared CDF takes in always a lower bound, an upper bound, and a degrees of freedom. So I didn't mention this before, but there is a degrees of freedom for chi-squared tests that should be stated with your important numbers. And what your degrees of freedom is equal to is not your sample size minus 1, but your number of categories minus 1. So even though we have 256 CEOs, we have 12 categories because there's 12 zodiac signs. So our degrees of freedom will not be 256 minus 1, but it will be 12 minus 1. So number of categories, not number of subjects. So you'll notice that we have a chi-squared CDF that is apart from our TCDF and norm CDF. So do you remember in the first place why we split up the norm CDF and TCDF functions? That's because the norm CDF uses a normal model as a reference and a TCDF uses the T model as a function. So why do we have a chi-squared CDF as well? This is because chi-squared is yet another type of distribution that is set apart from the shape of a normal distribution or a T distribution. So what a chi-squared distribution generally looks like is something like this. So your chi-squared value will be some number along your distribution, and then what you will always do between your 5th and 6th step will be to flag your chi-squared statistic and then shade in the area from your chi-squared to infinity. There is no nearest extreme in this one. You will always go to infinity. You can forget going in this way. Never go in this way. Always go towards infinity for your chi-squared statistics. And there's a reason for this. Because when we calculated our chi-squared statistic, we squared this top value. Once we squared this, that means we got rid of any negative or positive directions. Everything will always be going in one direction because everything has already been turned positive. So chi-squared is always going to be a one direction test. With your chi-squared shape, you will notice that we don't have a mean or standard deviation here. So what defines this model is your degrees of freedom. So as your degrees of freedom increases, like the T model, your chi-squared model will look more and more like a normal model. But unlike your T model and your normal model, the chi-squared model does have a lower bound. Your T model and normal models go on forever in both the positive and negative directions. Your chi-squared model cuts off at 0 because your chi-squared statistic will always be positive. So here is our hypothesis test for today. Again, we're still doing the same company CEO problem, and we're going to test and see if CEO birth is evenly distributed throughout zodiac signs. So our first step is to list what we are interested in. So our POI, we would say something like, we want to find if CEO birth is evenly distributed throughout zodiac signs. So there we go. Our step 2 would be to list our important numbers and our hypotheses. So our hypotheses, again, we can do those first actually because those are easy to write and they've already been set. So CEO birth is evenly distributed. And for our alternative, CEO birth is not evenly distributed. Our alpha value, so our threshold is 0.05. And we also need to give an expected value in the degrees of freedom. So our expected value, or E of x, is equal to, we calculated this earlier actually, so it's just the 256 total CEOs over the 12 zodiac signs, so 21.33. And then our degrees of freedom is the number of categories minus 1. We have 12 categories for 12 zodiac signs, so 12 minus 1 is equal to 11. So that's our degrees of freedom. This may be optional based on what kind of instructor you have, and this is to make our bar chart, and then put a line through it for your expected value. Next we have our conditions. So our first condition is just, is the data counted or not? Yes, the data is counted. Next, we ask ourselves, is the sample randomly selected and or is one person being a CEO going to have anything to do with another person being a CEO? Well, coming back up here to our original problem, we see the word randomly, so that basically takes care of two conditions in one go. So what we would write is, because the sample was randomly selected, the zodiac sign of one CEO should not affect the zodiac of another. So that takes care of randomization and independence. Next is 10%. So did we sample under 10% of the CEO population? We have 256 CEOs here. There's definitely a lot more than that on Earth, so yeah, I think we're good. And finally, we have our large enough condition, or expected cell condition, and that's the one that says we have to have an expected value of at least 5 in each cell. Well, we know that the expected value for each cell is 21.33, and that is definitely greater than 5, so we have passed that condition as well. And to conclude, we say the conditions are satisfied and we are going to proceed with a name of test. Because the conditions are satisfied, we can proceed with a chi-squared goodness of fit test. So our goal now is to get that test statistic, or our chi-squared statistic, so that we can plug it into the calculator to get our p-value. So the formula for our chi-squared statistic is equal to the sum of, for every category, the observed data minus expected data squared over the expected value. So that would be taking in all the categories, 23 minus 21.33 squared over 21.33. I got the 23 from our first category, and then adding it up for every single category. So we would do 20 minus 21.33 over 21.33, and then we would do the same thing for every single one of these categories. It comes out to be 5.094. So that is our chi-squared statistic. Putting that into a graph, that would look like this. Again, chi-squared graphs always start from 0, and then our graph looks something like this. let's say it's 1, 2, 3, 4, 5. I really have no idea where the 5 goes. We flag our 5.094, and then we shade in everything from here to the positive extreme. It will always be towards the positive extreme, never go in the negative direction. So this is the area that we're interested in, so it gives us a model for what we're going to do in our calculator step. So what we're finding is the probability that the chi-squared statistic is 5.094 or more extreme. So chi-squared is greater than 5.094. That is equal to our calculator function, this is the new one, of chi-squared CDF, putting in a lower bound, an upper bound, and a degrees of freedom. The degrees of freedom we have down here, and it was given in our second step for our important numbers, that is 11. And then looking at our drawing of the chi-squared model, we can see that our lower bound is 5.094, and our upper bound is infinity. Just a quick note, for any chi-squared test of this type, your chi-squared statistic will always be your lower bound and infinity will always be your upper bound. So putting this all into the calculator, we finally get a p-value back, and it is 0.9265. That's pretty big. That is really close to 1. So we probably know that we're not rejecting our null hypothesis already, because 0.9265 is really big compared to alpha, which is 0.05. So with that, we can conclude. So if CEO births were truly evenly distributed among zodiac signs, the probability of the observed data or more extreme occurring would be 92.65%. Because the p-value is so large, and then we do our comparison, 0.9265 is greater than alpha, which is equal to 0.05, I failed to reject the null. So usually we end out here for our videos with our hypothesis test, but there's more, so hang in there. So in past videos, we have worked with 1 proportion or 2 proportion tests. Chi-squared tests actually have another purpose, and they can be used to perform tests on multiple proportions. So it generalizes our proportion hypothesis test to any number of proportions. So here in this case, we have a contingency table or a two-way table, and we will be comparing all of these proportions here. So we will be turning all of these counts into proportions and using them for a test to see if major has anything to do with your future plans. So if you go and get a job, go into grad school, or some other choice. So with a contingency table, what we are running here is no longer called a chi-squared goodness of fit test, but this is now called a chi-squared test of homogeneity. The conditions to run this one is actually the same. It's just your counted data, independence, randomization 10%, and expected cell frequency. So that is the expected value of at least 5 in each cell. So what you have in a contingency table that's different from our old simple table is that the expected value is not the same for every single cell. So there's multiple steps in doing this. This over here is our original table, and what we do first is we turn everything into a proportion. So this bottom row all turns into our 100%. This is our totals. So the total number of people is 1,456. That means 685 people out of everyone that was in this survey chose to go directly into employment. And so that way we can have a proportion. So this box becomes 685 over 1,456, and this box becomes 466 over 1,456, and so on. And over here we would do the same thing. So this box would become 209 over the total number down here, so 448. And doing that for every single cell, we come back with this table over here. So now that we have our table of proportions, what can we do to get our expected values? So what we're basically trying to find here is if the distribution is even and if there's no association between what major you do and then what you choose to do after college. So if that were true, then that means no matter which major you go into, the same percent of people for every major go directly into the workforce, the same percent of people go into grad school, and the same percent of people go do other, if there was really no relationship between major and then whatever you do after college. By extension, that means that your total percentage of people that go into the workforce, so 47%, should be constant throughout this entire row. So these should all be 47% if there was really no relationship between major and whatever you do after college. So what we do is we take that 47% and we apply it to everything on this row. So everything on this row should be 40% of their total bottom row. So this box right here, the 209, now becomes 448 times 47%. And that gives us our first box in our expected value table, 210.769. And then we come over here to our next box. So again, we multiply 47% from here to this 484 and we get 227.706. So we're not doing any math on these numbers per se, we're doing it all on the total numbers. These are our observed values and we're going to be comparing it to our expected values. So doing this for everything on our first row, we get our 175.995 and 70.57. Going on to our next row, we have 32% here. That means we take our 32% and we multiply it to our first total, so 448 times 32%, and we get this box. So we do that for this row too, and then we come down with our 20.9% and we get this row as well. So this is our expected values table. Using this table, we can compare it to our original table and then create our chi-squared statistic and get our p-values. So here I took out our intermediary proportion table. Now we just have our original table and our expected values table. So how do we get the chi-squared statistic? The main principle is still the same. It's always going to be the sum, and then for every cell, observed minus expected squared over expected. So we can ignore these boxes for now because our observed data is going to be everything on the inside. So you can ignore the stuff on the margins. The numbers on the inside are the ones that we use for our chi-squared calculations. So this is our observed table and this is our expected table. So for each observed value, let's take the first one of 209. We subtract from 209 the expected value for that same cell. So we come to our expected values table and this is the corresponding cell. So 210.769 is the expected value for this cell. So we subtract 210.769 squared over and then our expected value again of 210.769. And then we do this for every single cell inside our rectangle here until we get to our last one, which would be 16 minus the expected value of 31.422 squared over 31.422. So adding everything up, we get a final chi-squared value of 93.66. So we have our chi-squared value. What about our degrees of freedom? So the degrees of freedom here, it's not equal to the number of cells anymore. It's equal to the number of rows, so R for rows minus 1, times the number of columns minus 1. When we talk about rows and columns here, we're going to ignore the total row and the total column. So we can ignore this column and this row. All we care about is this inside stuff. So here we have 3 rows and 4 columns. So our degrees of freedom is equal to our 3 rows minus 1 times our 4 columns minus 1, which is equal to 2 times 3, and that is equal to 6. So we have 6 degrees of freedom. So we have the chi-squared statistic from earlier of 93.66, and we have our degrees of freedom now. So that means that we can now get our p-value. So our model now looks something like this, with 6 degrees of freedom, and then our, let's say the 93 is out here. So our chi-squared value of 93.66, and we shade in everything from here to infinity because chi-squared models always go towards infinity. So this is the area we're interested in. To get that, we write probability that chi-squared is greater than 93.66 is equal to, and then we put in our calculator language. So chi-squared CDF, and then we put in a lower bound, upper bound, and degrees of freedom. So degrees of freedom we got is 6, and then for a range of numbers we're going from our chi-squared value to infinity. So 93.66 to infinity. and that gives us a very small number. It is around insert 17 zeros and then 525. So we already know that is incredibly small, so here we would reject the null and we would say that there is a relationship between major and what you do after college. So there was a point in time, especially back in linear regression, when we mentioned residuals. So our residuals is equal to the observed data minus the expected data. So coming back to these tables, each of the cells has its own residual. So the residual for cell number 1 here would be 209, the observed data, minus the expected value of 210.769. Then the residual for arts and science majors that go into the workforce is 198, so the observed data, minus 227.706. So what can this tell us? The first thing that you can do with a residual when you're working with contingency tables is to standardize the residual. So standardization we have used before when we talked about creating z-scores. So we transform everything into some sort of z-score so that we can evenly compare everything. So a standardized residual looks like this. It is noted with a C and then it is equal to the observed data minus the expected data. So your residual over the square root of the expected value. This formula should look very, very familiar because we've used a variant of it to calculate our chi-squared statistic. So our chi-squared statistic is equal to, again, observed minus expected squared over the expected value. So what is the similarity you see between these two formulas? Our standardized residual is just equal to the square root of the component that we use to calculate our chi-squared statistic. So if you take the square root of this thing right here, you will get the formula for the standardized residual. So once you get the standardized residual, you can put it into yet another table. And so now the work has already been done for you. These are your standardized residuals, and they're all in z-scores. What is one thing that you immediately know for z-scores? Anything above 3 seems to be a very unusual and extreme value because according to the empirical rule, once you go outside of 3 standard deviations, there's only a 0.3% chance that you will get a data point out there. So looking at our standardized residuals table here, we can see that this value here is very close to 0. That means the value of the observed data was very similar to the expected data. So there's nothing weird with values close to 0 like these. Honestly, anything within 1 to 2 standard deviations probably isn't anything that we need to really pay special attention to. But then you start seeing these 4s here. This 4.44511 and this 4.24817. What this incredibly small z-score tells us is that the number of engineering students that did not go to either the workforce or grad school, they chose the other option, is much lower than expected. And what this positive extreme z-score tells us is that the number of agriculture students that don't go directly into the workforce or to grad school is also much higher than expected. So any negative standardized residual tells you that the observed data was lower than expected, and any positive standardized residual tells you that the data was higher than expected. But if it's close to 0 or around 1 to 2, you can probably disregard it. It's probably just a sampling variation that you're bound to get. It's very rare for you to get a table of just zeros. That would be ideal, but still very unrealistic. You're going to get a lot of z-scores that are not equal to 0. As long as it doesn't go above 3, you can probably chalk it up to just your normal sample-to-sample variation. That's it for chi-squared. Next video we will go into linear regression, so I'll see you guys there. Thanks for watching. Hope you learned something. Peace.